Hello class, Mr. Cordova here bringing you section 7-3 tangent lines. Let's get to our lesson objectives. And our lesson objectives state to use the relationship between a radius and a tangent and to use the relationship between two tangents from one point. So what exactly is a tangent line? That's what we're going to be defining right now. So a tangent line is a line in the plane of the circle that intersects the circle in exactly one point. The point where a circle and a tangent intersect is known as the point of tangency. Point of tangency. So now that we have those two defined, we're looking here at the diagram here on the left. We have a blue circle and our reddish kind of fuchsia kind of colored line AB, and line AB intersects the blue circle at exactly point B. So point B is our point of tangency and AB is our tangent line. So let's take a look at our first theorem. So Theorem 7.5 states if a line is tangent to a circle, then the line is perpendicular to the radius drawn to the point of tangency. So if I take a look, if AB in this diagram happens to be tangent at point P, then the intersection between OP and AB right here forms 90-degree angles. So those two angles, I can say the angle OPA is 90 degrees. And I can also say that angle OPB is also 90 degrees. We have those two. And now that we have that defined, let's take a look at some examples. So here we have example 1, finding angle measures. ML and MN are tangent to circle O. Find the value of x. So if we take a look at the diagram, we see that angle x, or x actually, is an angle. So that means it's in degrees. Our answer needs to be in degrees. And we see that OL is a radius and ON is also a radius. And we see that the two intersect, OL and LM intersect. ON intersects MN. So that means if these two, LM and MN, are tangent, that means that this angle right here is 90 degrees and this one over here is 90 degrees. The figure formed by the two radii and the two tangents, if you take a look closer, it is a quadrilateral. So we know that a quadrilateral, its interior angles add up to 360 degrees. So we can say that angle O plus angle L plus angle M plus angle N equals 360 degrees. Then we go ahead and substitute those values. For angle O, they're telling us that it is 117. For angle L is 90 degrees. For angle M is x. And angle N is also 90 degrees. And that equals 360 degrees. We go ahead and combine like terms, and we end up getting 297 plus x equals 360. Then we go ahead and subtract 297 from both sides. And we get that x equals 63 degrees. That is one way to do this. There is one property that we can actually use on this particular type of problem that requires a property, and I'm going to show you what that property is in this box up here. And it goes like this: x equals the major arc minus the minor arc divided by 2. And that is unique to two tangent lines and point M right over there. Unique. So the major arc, if you remember, a major arc consists of an arc whose central angle happens to be greater than 180 but less than 360 degrees. We happen to have such an arc over here that goes from L all the way to N. I also mentioned that a major arc usually has 3 points. So for the sake of illustration, I'm going to put a point here and call it point, let's see, P. So that's our major arc. Therefore, if that's our major arc, we know the minor arc over here happens to be 117 degrees. So from L to N, this arc over here also measures 117 right here. And if you know that between the minor arc and the major arc forms a full circle, that means that the remainder, this major arc over here, is the difference between my minor arc and 360 degrees. So I can say, and I'm going to do the calculation down here, x equals the major arc, 360 minus 117, so we have 360 minus 117 happens to be 243. So the major arc right here, which is, I'm going to say arc LPN, so LPN, major arc LPN, the arc symbol LPN is 243 degrees. Okay, so now we plug that in. So we have 243 degrees minus the minor arc. The minor arc is 117. And we're going to divide that by 2. So we come over here and we say 243 minus 117 happens to be 126. Divide that by 2, and that comes out to be 63 degrees as well. So we have 63 degrees here, 63 degrees right here. So we have two ways that we can actually calculate that angle if we actually needed to do so, like in this problem. Okay, now part B is yours. So I'm going to read it, then you're going to pause, try the problem, and then see how if I get the answer that you also get, or if you get the answer that I get. So let's take a look. ED is tangent to circle O. Find the value of x. X again is in here as an angle, so that means that it's in degrees, and my measurement needs to be, my answer needs to be in degrees. So let's take a look. Figure it out? All right, let's take a look. The triangle that we have there, if you notice so far, we have from D all the way down here. This right here is a diameter. So we have here half of the diameter is my radius, so I have DO. DO is a radius, and we have that ED right here. ED is a tangent, so that means that this angle right here is 90 degrees. Then we can go ahead and make a relationship and say that 38 plus angle D plus angle E equals what? Well, if you recall from the triangle angle sum theorem, the interior angles of any triangle add up to 180. So that's why I started adding all these. So it is 180 degrees. Then we substitute the 38 was given, so we'll substitute what we have. Angle D we know is 90 degrees because it's a tangent line through the radius, plus angle E is X. And we go ahead and do equals 180. We combine like terms. 38 plus 90 is 128, plus X equals 180. Then we go ahead and subtract 128 from both sides, subtract 128 from both sides, and we end up having that X equals 52 degrees. 52 degrees. And that's the answer right there. All right, moving on. Here's another problem. So let's take a look. It says a dirt bike fits tightly around two gears. The chain and gears form a figure like the one on the right. Find the distance between the centers of the gears. So we need to find the distance right here that I'm about to draw. Right, almost right there. There. That distance right there is what we're trying to find out. I'm going to label that distance D. Let me actually draw a better D. There you go. D. So let's see how we do this. We can, since the distance right here, well actually the line, the one that is here 26.5 is tangent to both circles, and we have a radius of 2.4 here, and they intersect the radius right here. Notice that they make 90 degrees on both sides, here and there. I can slide that line to the center of the smaller circle so that the new line that I'm going to draw, my auxiliary line, is parallel to the tangent line that measures 26.5. Right there. And that sort of resembles, well, this line, first of all, is parallel to this line. So if this angle is 90 degrees, this angle right here is also 90 degrees. And now we're left with a right triangle in which D, since my 90-degree angle is down here, D is the hypotenuse of my triangle. So we need to do some Pythagorean theorem to this problem. But first, we know that this length over here, the one on the back, is 26.5, just like the original. So it's 26.5 here. But this length over here is no longer 9.3. We move the line the same amount as the radius of the smaller circle. The radius of the smaller circle is 2.4, so we need to actually subtract 2.4 from 9.3, and that gives me 6.9. So this length down here now is 6.9. And we can use the Pythagorean theorem. Pythagorean theorem tells me that the hypotenuse squared, which is d squared, equals 6.9 squared plus 26.5 squared. 6.9 squared equals 47.61. 47.61 plus 26.5 squared to be 702.25. That means that d squared equals 749.86. Then we take the square root of both sides and we get d equals the square root of 749.86. And when we actually punch that into a calculator, we get a number that goes 27.3836 and a bunch of something else. But our answer, it doesn't specify to what do we need to round, or we need to round, or what do we do. So the rule of thumb that I have mentioned to you guys in the past is that you take a look at the information that they give you. And if you notice, this is 26.5 over here, this is 2.4 over here, and 9.3. That means that our values are to the 10th place. So my answer should reflect the information that they give me. So I'm going to round this to the 10th place, just like the information that they give me. So this rounds up to approximately 27.4. And the units are all in inches, so my answer is also in inches. And here is my answer. All right. Now let's take a look at the problem you're going to be working on. Part B. As soon as I finish reading it, pause the video and see if you can get the same answer that I will be getting. And it goes, a belt fits tightly around two circular pulleys as shown at the diagram, at the right rather. Find the distance between the centers of the pulleys. Good luck. Okay, now let's take a look at this problem. So it's very similar to the one that I just did a second ago. So essentially, we are going to go ahead and find this distance from the two pulleys. So we're going to make the line that we're going to be calculating right there. Actually, that looks better. All right. So now I need to move the line that's tangent right here, and I know it's tangent because there's 90 degrees at the intersection between the radius and that line. So I can actually move down that 35-inch line, tangent line, to where the center of the smaller circle is. So, and also be parallel to the original line. So we go over here and we make our line. As parallel as possible. All right. Since I moved it and this angle is 90 degrees, this angle over here is also 90 degrees. This line that I just made also measures 35 inches. We're trying to calculate D right there. The length right here is no longer 14 because I moved that line the same amount of distance that this small circle's radius, which is 8 inches. So I take 14 and I subtract 8 and I get 6. So this little length right here is 6 inches. All right, then we're going to be using the Pythagorean theorem because D right now is the hypotenuse, my 90-degree angle right here, and the side opposite the 90-degree angle is my hypotenuse, so I can say that D squared equals 6 squared plus 6 squared plus 35 squared, and we have D squared equals, let me make that 6 a little bit better, 6 squared rather. So 6 squared is 36, 35 squared is 1225. That gives me that D squared equals 1261. Then I take the square root of both sides and I get that D equals the square root of 1261. And this equals 35.5106 and a bunch of numbers after that. So I need to see if I need to round it up, and the instructions doesn't say to round it up to anything in particular, but if I look at the information given, all of them are whole numbers. So that means I'm going to round this up to my nearest whole number, and the nearest whole number, 35.5, all this rounds up to 36, and my units happen to be inches. And here is my answer, 36 inches. All right. Moving on to our next theorem is theorem 7-6, which is the converse of our previous theorem that stated, well, this one states, if a line in the plane of a circle is perpendicular to a radius at its endpoint on the circle, then the line is tangent to the circle. The other theorem stated that if a line is tangent to a circle and that line intersects the radius, then the angles at the intersection are, or the angle at the intersection is 90 degrees. This one states that if the angle of intersection between the radius and a line going through that point is 90 degrees, if that angle is 90 degrees, then the line itself is a tangent line. So let's take it from there and go into our next example. And we have this problem over here. And it says, is ML tangent to circle N at point L? Explain. So we take a look at this problem, and we're trying to prove that this angle right here at L, this angle right here is 90 degrees. We don't know if it's 90 degrees. We're trying to prove it if it is. So back when we were dealing with right triangles and the Pythagorean theorem, there is a way to prove whether a triangle is a right triangle using the Pythagorean theorem. And it goes something like this. I need to find out which of these three sides would be, assuming that it's a right triangle, which side will be my hypotenuse. So since I'm trying to prove that angle L right here is the one that is 90 degrees, the side opposite it will be this 25 right over here. So I'm going to hypothetically use this as my hypotenuse. So we're going to say 25 squared equals, and that it equals question mark because we're trying to test if that's true, equals question mark 7 squared plus 24 squared. We're trying to find out if that is true. If that is true, we are golden. So let's take a look at this problem and see how that goes. So we have 25 squared is 625. Question mark, 7 squared is 49. Plus 24 squared is 576. Then we have on this side 625. That equals, because 49 plus 576 happens to be 625, so it actually checks out. So this triangle right here indeed is a right triangle. Therefore, that line ML is tangent. So we can say yes. Reason? Because triangle NML is a right triangle. Is a right triangle. And that's why. All right. Part B is yours, and I'm actually going to leave it right here because you're going to be using the same diagram that I did. So as soon as I finish reading it, pause the video and try to see if you get it. So here goes. If NL equals 4, LM equals 7, and NM equals 8, is ML tangent to circle N at point L? Explain. Pause it now. All right, let's see if we can actually come up with the answer for this one. This one is pretty much the same process, except that we're using different numbers. So we actually have our supposed hypotenuse now is 8. So we have 8 squared equals question mark 4 squared plus 7 squared. A squared is 64 equals question mark 16 plus 49. And then we have 64 over here, and 64 is not equals 65. So that means that the ML is not a tangent because triangle NML is not a right triangle. And that's the answer for that one. All right. Moving on to Theorem 7.7. Theorem 7.7 states that two segments tangent to a circle from a point outside the circle are congruent. In other words, AB right here is congruent to BC, so I can say that AB is congruent to BC. That's what the theorem states. All right, let's take a look. We're here back to our bicycle chains. So it says the diagram represents a chain drive system on a bicycle. Give a convincing argument that BC equals GF. A convincing argument. Essentially, we're almost doing a proof, but I'm going to approach it in a different way that is almost like a proof, but not that formal. So the first thing that I'm going to do is I'm going to redraw the diagram here for the sake of illustration. It's not going to be pretty, but at least something like this. Circle here and a circle here. And then we have our tangent lines here and our tangent line over there. And then we have point B right here, point G right here, point C right there, and point F right there. So we have, this is going to be, oh, got rid of my circle. There you go. So this right here is 90 degrees. This right here is 90 degrees. This right here is 90 degrees, and this right here is 90 degrees. All right, told you it was not going to be pretty, but here it goes. So the first thing that I do, I can make a point H outside the small circle right here, like so. Point H over here. And then those are two auxiliary lines that are going to help me in a little bit. And we can actually start by going like this. HC equals HF, right? That is true because the theorem 7.7, right? HC, this full new line that I just made, HC is equal, or actually might as well just say congruent, is congruent to HF because of theorem 7.7, right? So now we can actually now say, because of the segment addition postulate, we can say that HB plus BC equals HG plus GF right? So we have that, and this is the segment addition postulate. we can now say that HB equals or is congruent to HB is congruent to HG, and that is also because of the theorem 7-7. So take a look. HC and HF are congruent because in reference from point H to the big circle, these two lines are tangent and point H is my point outside the circle. HB and HG are congruent because in reference to the small circle, point H is a point outside the circle that goes through two tangent lines, right, of the small circle. So that's why that is. Then we can just go ahead and on this second line, since HB and HG happen to be congruent and they happen to be on both sides of my equation, I can just get rid of it and I get that BC equals or is congruent to, in this case, to GF. And the reason is called the subtraction property. Subtraction, if I can spell subtraction would be great. Subtraction property of equality. All right. Now that we have that one, let's take a look at part B. And part B actually uses the same diagram, so I'm going to leave it there. As soon as I read it, you know the drill. So it goes. Give a convincing argument that BC equals GF above if you know that BC, line BC, and line GF never intersect. Pause the video and good luck. Okay, so in this particular case, it says that if you know that BC and GF never intersect, and they are on the same plane, that means the two lines are parallel, right? The two lines therefore are parallel. So if they are parallel, that means that the distance from them is the same. So that means that the two circles have to be the same, so they look something like this. One circle here, as congruent as I can get them. Let's see if I can make that better. That looks a whole lot better. So we have the chain supposedly goes right here and it goes right there. We have point B here, point C, point G, point F, and we have our radius. Now, right here, this radius is right here. Oh, actually, that's a diameter now, right? So if that's the case, and it is parallel, that means that the distance from B to G has to be the same as from C to F. And if they're tangent, still tangent, that means that this angle is 90 degrees, this angle is 90 degrees, 90 degrees here, and 90 degrees here. And lo and behold, the figure that actually gets created is a rectangle. And a rectangle happens to be a parallelogram. And in a parallelogram, we know that opposite sides happen to be congruent. So in this case, we can say if BC, or line BC, and GF never intersect, I actually spelled never, that looks like Neve, never intersect, then BC FG is a rectangle rectangle. Let me fix that, rectangle. And then we can say a rectangle is a parallelogram where opposite sides are congruent. That means, and if you can see, BC and GF are opposite sides on the new diagram as per description. So we can say, and that's our proof, that they actually are congruent. All right, that was that example. So let's take a look at what's next. Now we have inscribed polygons. Now we discussed what inscribed means. Inscribed means particularly circles. An inscribed circle means that the sides of the triangle are tangent to the circle inside. So let's take a look. It says circles inscribed in a polygon. Circle O is inscribed in triangle ABC. Find the perimeter of ABC. So we have that. Take a look at the diagram here on the right, and a few things. By telling you that is inscribed, we know that points A, B, and C are points outside the circle, and we know that the segments AD, AF are tangent to that circle. Segments FC and CE, actually CF and CE, are tangent to that circle. Same thing as sides or segments BD and BE are tangent to the circle. So if we go ahead and go over the definition or the properties of tangent segments here, we can say the following. We can say that AD, well, AD, they tell us what it is. AD is 10, but AD is equals, or let me just say congruent to AF. And AF, therefore, is also 10 as AD is. Then we can say that BD is congruent to BE. You write a BD. BD, we know that BD is 15, so that means that BE is also 15. Then we have CF. CF is congruent to CE. And those happens to be 8. And these are in centimeters, right? So it's centimeters here, and centimeters there. Perimeter means I'm going to add, in this particular case, it's a triangle, so I'm going to add all three sides. So my perimeter, P, equals AB plus BC plus AC. Okay? I'm going to actually express this using the segment addition postulate by expanding it a little bit. AB happens to be AD plus BD. BC happens to be BE plus CE. And AC happens to be AF plus CF. All right? So then we go ahead and substitute the values, and we get that perimeter equals AD. AD is 10. Right here, we see AD is 10 right here, see it? And then we get plus BD. BD is 15. plus BE, BE is also 15, plus CE, and CE is 8, plus AF, AF is 10, and plus CF, which is 8. When we actually add all that up, we get our perimeter happens to be 66 centimeters. And that's that one. All right. Now, part B is all yours. So I'm going to read it here. It says, circle O is inscribed in triangle PQR. Triangle PQR has a perimeter of 88 centimeters. Find QY. Good luck. All right. This particular problem is different because they already give me what the perimeter is, and I'm trying to find out what QY is right over here. So let's actually take a look at this and do a similar relationship that we did earlier on the other problem, but we're going to apply it here. Again, points P, Q, R are points outside the circle, and they intersect the tangent segments or the tangent sides on the circle. So let's take a look. So PX is congruent to PZ, and that equals 15. Then we say that QX is congruent, actually write a better congruent to QY. We don't know what either of those two happen to be. And then we have RY is congruent to RZ. And that equals 17. That equals 17 right there. Now, our perimeter looks like this. P equals PQ plus QR plus PR equals 88 centimeters. So here's where it gets interesting, and this is something that I'm going to do, and I'll explain it why I'm doing it. PQ, using the segment addition postulate, PQ is PX plus QX, isn't it? But isn't QX the same thing as QY, which is the one I'm looking for, right? I really don't care to find out QX. It's really not important. The question asks to find QY. So for the sake of formula, I'm going to replace, instead of QX, I'm going to say that it's PX plus QY. Okay? Then we have QR, and QR remains as QY plus RY plus PR. PR happens to be PZ plus RZ. And that should give me my 88. I'm going to go ahead and put the 88 over here, centimeters. Then we go ahead and start substituting stuff. For PX is 15. So this is 15 right here. QY is what we're trying to find out, so it remains as QY. Plus QY over here, QY. Plus RY is 17. Plus PZ is 15. Plus RZ is 17. And all that adds up to 88 centimeters. So we combine like terms, and when we combine like terms, we are left with 2QY equals, not equals, 2QY plus 64, that looks like a 20, 2QY, that's better, plus 64 equals 88, like so. Then we subtract 64 from both sides. And we get that 2qy equals 24. Then I'll divide both sides by 2, divide both sides by 2, and I get that qy, which is what I'm looking for, equals 12. And the units here are 12 centimeters. And that's the answer to this problem right there. All right. And that wraps it up for this lesson. If you have any questions, feel free to email me or send a message through Teams. See you next time, guys.